Oh, reload. Where? Oh, where? Oh, okay. Okay, it's here. Okay, let's get started. So, I guess before we start, any question from this time? Today we will talk about this. Yeah, we'll go over this periodic, discrete, and complex exponential carefully again. But I guess before we go to the what's going on? Okay, yeah, before we go to derivation, let's talk about this new slide. This is something that we were thinking about implicitly, but let's make sure everyone understands this. Okay, so the question is how we visualize those periodic complex exponentials. So let's go back to continuous one first. Okay, so this is a mental picture I usually have. So those periodic complex exponential are basically functions of this form e to the j omega t. Obviously, there are going to be coefficients sometimes, but let's think about e to the j omega t first. Okay, and so what's e to the j omega t on complex plane? So the first way to visualize this thing is thinking about it on complex plane. And well, this is in polar form, so you can think about this e to the j omega t point. So this z is e to the j omega t. It has some r and it has some omega t. And so r will be 1 because we have 1 here. And this omega t will obviously increase with time. And so so this complex point will move on this unit circle throughout time because omega t is going to increase with time. And your e to the j omega t will be running on circle on this complex plane. Okay, so omega t from 0 here and pi over 2, omega t equal to pi and 3 pi over 2 and 2 pi. Okay, and yeah, so this is how it's being periodic on complex plane. This e to the j omega t just keep going on circle. And but another way to visualize this, and I will do a lot, is try to draw this as a 2D picture. Because you think about it, circling on complex plane, you don't really see a t, right? You need to think about this moving through t. And usually we like to draw a signal like a picture like this. And what we do is we will use the Euler's relation. So Euler's relation once again says e to the j theta equal to cosine theta plus j sine theta. And you just apply this on your e to the j omega t, then you see e to the j omega t is cosine omega t from j sine omega t. So you can plot the real part and the imaginary part of your e to the j omega t. So you can also kind of see it on plane. So you walk wrong. This e to the j omega t point running on circle, and the real part will oscillating back and forth with a cosine omega t, and the imaginary part will oscillating back and forth as sine omega t. Okay, so sine oscillate like this. When omega t equals 0, it's from here, then going up, going down, and going back. Okay, and yeah, so sometimes we will schematically, although this is not quite e to the j omega t, but when we think about e to the j omega t, we'll plot the sinusoidal function here. So either cosine omega t or sine omega t, and the cosine omega t look like this, and the sine omega t look like this. So yeah, they oscillating up and down, up and down. Okay. So any question from this extra slide so far? No. Okay. Yeah. So these are the two ways you can visualize e to the j omega t. Is something that's running in circle on your complex plane, or you can think about its real part and the imaginary part oscillating like a sinusoidal. Okay. Okay. Then let's go back to once again this derivation about periodic discrete time complex exponential. And as we said, we want the discrete, we want the complex exponential to be periodic for discrete time. Then it's more complicated. So you need to satisfy this periodic equation. So your x of n plus big N equal to x of n for very small n. Then you plug in. Then you see this e to the j omega naught n should equal to 1. Okay? And the tricky thing is that this big N need to be an integer. And this is spatial, unlike in continuous time. So let's see like some continuous time signal with a different frequency. So you see that these are continuous time signal, and as you increase their frequency, they are always periodic, right? So those are 3 continuous time signal with increasing frequency, and you see they are always periodic. The period just getting smaller and smaller. But when you write the same formula and thinking about they as the discrete time signal, so what happens is you are going to kind of take sample points, right? You are going to kind of taking sample points at because we say for the discrete signal, you always sample at these integer values. And what happens is this T3 might not be an integer value, okay? And so this T3, T2, T1 might not be integer value. So you need to have some integer value that actually matches the sum of your big T here. So maybe this is not an integer value, but maybe like a 2T1 this will hit some integer point, and then this will be your n, for example. Okay, and yeah, so let's see that in more detail. And so we want to make that intuition in mathematical form. Then we solve those algebra. So we start with this e. So for some n e to the j omega naught n e to equal to 1, and so we go back to this. We see that e to the j omega naught n equal to 1 means that so this e to the j omega n is you are running on this circle, and equal to 1 only when you go back to the full cycle, right? So this j omega naught n need to be some multiple of 2 pi for you to run back to this point. Okay. So you see e to the j omega naught, this omega naught n need to be some multiple of 2 pi, and this multiple should be some integer. Okay. So omega naught n equal to 2 pi m, and so big N is an integer, and m is also integer. So once again, big N is an integer, because big N is a period for discrete time signal, and the discrete signal only have point on integers. So big N is an integer, and m is an integer because you need to run back to a full circle for this thing to be 1. Okay. So big N is an integer, m is an integer, and integer divided by integer is a rational number. So you see omega naught divided by 2 pi is a rational number for your signal to be a periodic signal. Okay. And so spoiler ahead, so if this is not satisfied, then your signal is not even periodic. Okay. But okay, so let's back to the periodic case. So if omega naught divided by 2 pi is a periodic signal, is a rational number, then we have a periodic signal here. Is small m divided by big N. And then we can find the fundamental period and the fundamental frequency. So what's the fundamental period? Fundamental period is the smallest possible n that satisfies this thing. Okay. And so you move things around, then you see big N is the smallest integer that is some integer n multiplied by 2 pi divided by omega naught. And hopefully, can people still see this? Is quite small. I guess I will spell them out. Okay, so let's see some example to get an idea of this equation. Okay? So as we say, we want omega naught divided by 2 pi to be some rational number. Okay, so omega naught is basically some rational number times 2 pi. Okay, I should type it here. Okay, yeah. So by this equation, another form is we have omega naught equal to 2 pi times some rational number, right? M divided by n. Okay, and let's say our omega naught have different value. So if omega naught is 2 pi times 2/3, then what's m and n in this equation? Anyone want to answer? It should be really straightforward. So what's this m here? Okay. If omega naught is 2/3 times 2 pi, and okay, yeah. Omega naught is 2/3 times 2 pi, then you just matrix this equation where omega naught is 2 pi times m over n. And yeah, so your n over n should be just 2 and 3. Okay? Yeah, so omega naught is 2/3 times 2 pi, then you kind of just eyeball this and see your m is 2. and n is 3. Okay, and but I guess I should put this second. And but we also say the smallest possible m. Okay, so smallest possible means that if you somehow want to write your omega naught as 2 pi times 4/6. Okay, and 2 pi times 4/6 doesn't mean your fundamental period is 6, because 4/6 actually equal to 2/3, and 4 and 6 is some coprime, right? Okay, so you want to write your 4/6 as 2/3. Okay, so with this 4/6, your m and n is still 2/3. Okay, so if for whatever reason this rational number here, your fraction is common factor, then you want to divide all the common factor first. Okay, so for this 4/6 equal to 2/3, and so your n will still be just 3. Okay, and there is another tricky point, which is we write the absolute value m here. Okay, and this is because your omega naught might be a negative number. So if your omega naught is minus 2/3, then then you can think about whether you want to put your minus sign on your n or minus sign on your n. And what you want to do is put your minus sign on your n, because we say because big N is a period, and we want our period to be a positive number. So n should be a positive number, so you should put this minus sign on your n. Okay, so if your omega naught is minus 2/3 times 2 pi, then your n should be minus 2 and n should be plus 3. Okay, question?
Can you define m and n again? M and n. What
N.
is the definition of m and n?
M and n is is like I guess we don't have I guess the definition is here, but it's a little harder to use. So you write your 2 pi divided by omega naught. Okay, so if you want a very precise definition, then first we know that omega naught divided by 2 pi need to be a rational number. Okay, so this is like a prereq. So omega naught divided by 2 pi is a rational number, and this is also a rational number. So 2 pi divided by omega naught is also a rational number. Then you want to find the smallest possible m, such that m times this rational number is an integer. Okay, and smallest possible m such that n is an integer. Smallest possible absolute value m such that n is a positive integer. But it's easier to see with this example. So omega naught divided by 2 pi. So just think about what is omega naught divided by 2 pi, right? So omega naught divided by 2 pi are those rational number. Then basically, then you take out the, then you kind of what's that called? So you take out the common factor, divide all the common factor over the upper part and lower part, and so you get those smallest possible ratio. And then m is basically the upper number, and n is the lower number, and n is going to be your period. Okay, and okay, so is that okay? Yeah, sure.
我想问一下物理意义，就是
物理意义。
为什么要这样子做？就是 m 除以 n，就是我有点搞不大懂，就是要怎么跟之前的想法结合？就是老师你在讲那个原本是在讲 continuous 嘛，在讲那个就大题，然后现在变成 m 除以 n 这件事情，那要怎么跟它结合？因为我一直卡住说 m 和 n 到底要干嘛这件事情。
m 和 n 要干嘛？
对。
这样比较数学。我想想看，我们后面会有例子，还是我们直接跳？有点像是说，我想想看，可能用这里来画图吧。例如说，对 m 的话，例如说我这个例子嘛，我这个例子，然后可能说。我这样子拉了2圈过来，然后这里是 n 这样子，对吧？然后可能是我想想看啊，然后这样子 m 会是2，然后例如说这里是 n 是5好了， 随便写。例如说这个例子，可能这样画比较快。例如说这个 n 等于5 ，because whatever，yeah。例如说这个 n 等于5，然后你发现我是绕了2圈上来才到这 n 等于5，那这里的 n 是等于2，这样没有比较清楚。就是可能这个是5嘛，然后我看看这要怎么切1、2、3、4，1、2、3、4这样的感觉吧。对，我 sample 这4个 point 这样子，然后 n 等于5的时候刚好绕了2圈回来，所以是 m 等于2。不行。对，
那不然老师我下课再。
对，好。对，但是数学上 ，OK，yeah，mathematically is like this，yeah，so I guess，yeah。The idea is kind of you take a sample point and yeah, because for the continuous point, you know that the period must be like your e to the j omega t. You want this omega t to be 2 pi, right? For your signal to come back to a period. But this omega t but omega t equal to 2 pi, but your t now need to be integer. So you're kind of sampling an integer point and you want at some point you hit an integer point. Yeah. Okay, I guess any other question? People question about the calculation? Yeah. Anyway, this is the period for discrete and complex exponential, and okay. And then there's a more confusing thing. Okay, then this is a fundamental period, and there's a fundamental frequency. So fundamental frequency is actually not equal to this omega naught anymore. So for continuous time, omega naught is just a fundamental frequency. But for discrete time, this fundamental frequency is 2 pi divided by n, just like before. And 2 pi divided by n, you see that it's not omega naught, it's omega naught divided by n. So the frequency is going to be slower than this omega naught here. Okay. Then I guess let's see some example where we don't quite have m here yet, but well, these are examples. Okay. So yeah, let's see some example of how the finite sampling give us a different result. Okay. So those are continuous time first. So as we see, so once again we see that for continuous time, if you increase your omega naught, then your signal oscillating faster and faster, right? So we have some omega naught here, 0 pi omega naught equals 0, and pi over 8, 1 over 8, 2 over 8, etc., all the way to 16 over 8, and you see your signal got oscillating faster and faster. Okay. And but let's think about the corresponding discrete signal. So we have continuous signal cosine omega naught t here. T can be whatever continuous number. And on the right hand side we have cosine omega naught n. So this n only taking point on integer values. Okay. So you see that the start they look quite similar. So when omega naught equals 0, we will have a constant signal here and a constant signal here. Okay, they look the same. And omega naught equal to 1 over 8. Then this continuous signal is going to oscillate like this. And well, the discrete signal kind of follow the same oscillation, although it only take point at this integer value. Okay. And omega naught equal to 2 pi over 8. Then you see that this oscillating well twice as fast. And this is also oscillating twice as fast. And yeah, and this says well, period is going to be smaller, right? So the period is going to be this. It's going to be, I think it's 4, right? So no, sorry, period is 8. But anyway, you see that this is oscillating faster, and this omega naught equal to. Oh, I guess we should also calculate the period here, right? So the period here, this is maybe this will serve some example, right? So omega naught here equal to pi over 8. So this is 2 pi times 1 over 16. So the period here is 16. So it's something like from here to here, then you should have 16 points. Okay, so just like here, the period is this, and then omega naught get higher, and this is 2 pi over 8. So this is omega naught is 2 pi times 1 over 8, and so your n should be 8, and it's like from here to here. So you should have 4 point here, 4 point here, and the period is 8. Okay, and then we have even higher and higher frequency, and omega naught equal to 4 pi over 8, and so this thing is no things are getting trickier, right? So 4 pi over 8 is 2 pi times 2 over 8, and as we say, 2 over 8, yeah, the period is not 8 anymore, it's actually 2 pi times 1 over 4. Okay. So the period is 4 here. So you can kind of see this. So the signal, because it's sampling so it's oscillating very fast. So the it actually sample at very discrete points. So it's like 1 0 minus 1 0 1 0 minus 1 0. So 1 0 minus 1 0 is 1 period. Okay, and yeah, so you see the period is 4 here. And then at this omega naught equal to 8 pi over 8, which equal to pi, then it got the highest frequency. As we say, for discrete signal, when your omega naught equal to pi, then it's highest possible frequency. Because your signal now is just 1 minus 1, 1 minus 1, 1 minus 1. And as you imagine, this is the fattest possible oscillation you can get on discrete signal. Because, yeah. So at one point it's 1, and the other point goes to -1. So this is the most change you can get. Okay. And once again, here the omega naught equal to 2 pi times 1 over 2. And so the period here is 2, because you got from 1 to -1, then that's 1 period. So 2.1 period. Yeah. 1 minus 1, then you repeat step 1, 1 minus 1, 1 minus 1, etc. Okay, and then things got funnier when you increase your omega naught even more. So omega naught equal to 12 pi over 8, and so this is 2 pi times 6 over 8, and so that's 2 pi times 3 over 4. Okay. So you see that your omega naught increase, but your period also increase. So your period start increasing, so and your fundamental frequency decreasing. Yeah. So this is the highest fundamental frequency, and then you see that here your omega naught is 12 pi over 8. Or the omega naught value is higher, and for continuous time your frequency is higher. But because you have this finite sample point, then you see that your period actually become 4 instead of 2. Okay? So period same as this. Okay? And you see that your signal are also kind of this 1 0 minus 1 0 1 0 minus 1 0. And yeah, so this period is 4 now. Okay. Yeah, so your period is 4 here, and so similarly, you see things kind of going reverse now. Your omega naught is 14 pi over 8. And so this is 2 pi times 7 over 8. So your period is going back to 8 now. And so this is kind of mirroring this one. Okay. Yeah. Oh, excuse me. Yeah. So this 14 over 8 signal, you see that it looks really similar to. Oh, excuse me. It looks really similar to this 2 pi over 8 signal. Is period 8, and this 15 pi over 8 signal, you see that it's really similar to this 1 pi over 8 signal with period 16. Okay. And finally, when your omega naught equal to 16 pi over 8, then you see that for every integer point, you are just getting 2 pi times n. So it's just going to be, right? So your cosine 2 pi times 2, you are just having cosine 2 pi times n, and it's going to be 1 always, okay? Because the signal here is just cosine 2 pi n, and you know cosine 2 pi n always equal to 1. Oh, why am I? Okay, something weird. Okay, anyway. What can I draw? Huh? What? Okay. Anyway, you know cosine 2 pi n equal to 1. Yeah. And excuse me. So, this. Okay. Yeah, cosine 2 pi n equal to 1, and you see that with this omega 9 equal to 16 pi over 8, even though continuous signal is a really phase oscillation, but because you always sample on the peak value, and so your discrete signal actually become a straight line. Is a constant function again. Okay. And then we start to, then if you increase your omega 9 even more, then we start seeing that why we say the frequency is periodic for discrete signal, because when your omega 9 is 17 over 8 pi, then the signal is actually exactly the same as if you subtract 2 pi from this. So this thing is equal to 2 pi plus 1 over 8 pi, right? Yeah, this is 2 pi plus 1 over 8 pi. So this signal is same as 1 over 8 pi signal. Wait, 16, I think, oh yeah. So this signal is same as the 1 over 8 pi signal. Okay. And this 18 pi over 8 signal, 18 over 8 pi signal, then is same as this 2 pi over 8 signal. So you see, if it's going to repeat itself, and this 20 pi over 8 signal, same as this 4 pi over 8 signal, etc. And yeah, then 24 pi over 8. So this is actually 3 pi over 8, and you see once again this is the highest frequency possible signal. So 1 minus 1, 1 minus 1, 1 minus 1, etc. And 20 pi over 8, 30 pi over 8. Then and finally at 32 pi over 8, then this is 4 pi, right? So you have a cosine 4 pi n, then you see that this is a constant signal again. Okay. Any question on these examples? Question? Okay. Okay. Yeah. And I guess now, okay, so quiz time. Yeah, so let's see 3 signal and compare their continuous time and discrete time difference. Okay, so we actually seen them previously. Okay, so first signal is so omega 9 equal to 2 pi over 12. Okay, so x of t equal to 2 pi t over 12, and x of n equal to 2 pi n over 12. And so you just read from here, you will see that t equal to 12, and so n also equal to 12, which should be fine. So you see that this one period has 12 dots. It has length 12, and yeah, so it's pretty obvious that n also equal to 12. And but now question is when your x of t equal to this 4 times 2 pi over 31, then if it's a continuous signal, then big T will be, well, big T is just 2 pi divided by this omega, and 2 pi divided by this omega is 31 over 4. But if you take this as a discrete signal, is your n also 31 over 4. So I guess let's ask this as a yes/no question first. If you think n equals to 31 over 4, raise your hand. Yes. And if you think it's not 31 over 4, raise your hand. Okay, some people wait. People want to answer yes no question. Okay. I guess let's think a little bit again. So yeah, yes no question. If you think n equals 31/4, raise your hand. And if you think n is not equal to 31/4, raise your hand. Okay, yeah, people know. So of those of you that say no, do anyone want to answer what's the period here? Yes. What's the actual n here? Yeah, it's 31. Yeah. And okay, so the next question. If your x of t equal to cosine 1/60, no, this is not the rational fraction of 2 pi. But anyway, you can still, for continuous time, it is still periodic. And t is 2 pi divided by 1/6, so it's 12 pi. And for discrete time, it's 1/6. So is n 12 pi here? You think yes, then raise your hand. If you think it's no, then raise your hand. Yeah, it's no. And what's the period here? Yeah, it's not periodic. Yeah, so people know. Okay. Yeah, so as we said, you want this omega naught divided by 2 pi to be a rational number. And so you can read your period from here. So omega naught equal to 2 pi and times some rational number. Then these rational numbers are n over n. And you want this m and n to be coprime. So you can read from here, this smallest possible n here, smallest possible positive n here will be your period. And if this is not a rational number, then it's not periodic. Okay. So it's written here. So our signal is like a constant exponential or a sinusoidal. They are very similar, exponential e to j omega n or cosine omega naught n. So your omega naught is 2 pi times rational. Then you can read your m and n here. You want the n is prime to n, and your n will be your fundamental period, and your fundamental frequency will be 2 pi divided by n. And it's not omega naught, it's omega naught divided by this n. Okay. And and if it's not a rational number, then it's not periodic. Okay. Here is the same thing, putting in a table, so I think I don't need to repeat it again. Okay. Okay, so let's go to an example. A bit more complicated example now. I think people can answer this. You are very good now. X of n equal to e to the j 2 pi divided by 3n plus e to the j 3 pi divided by 4n. Okay, so the first two questions should be very easy because they will do this a lot. So what's the fundamental period of this e to the j 2 pi divided by 3n? And you want to answer. So this thing is, I do a bit of calculation for you. So if you look at omega naught is 2 pi divided by 3, so it's 2 pi times 1/3. So what's n here? Anyone want to answer? So the period here should be 3. And similarly for this part, it should be also easy. So this part, the omega naught here is this is 3 pi divided by 4. And it's 2 pi times 8 over 3. Okay. And, I am doing calculation wrong. 2 pi times 3 over 8. Okay. And so what's the period here? Yeah, period is 8. And then the hot quadrant is, okay, so you got n equal to 3 here, and n equal to 8 here. And the hot quadrant is what the period for this whole signal. Okay, you want to take a guess? If one part has a period of 3 and another part has a period of 8, so one part repeats itself by every 3 dot, and another part repeats itself by every 8 dot. And want to take a guess? What's the period for the full signal? Yeah, so it's least common multiplier for this. Yeah, very good. So the answer is you have the least common multiplier of these two, and the fundamental period of both of them is 24. Okay. And then we have a wall of text to do the same calculation here. I think I can skip it a little bit. Yeah, so we have a slower derivation of everything. So here we kind of go in very algebraic. So what we do is we just plug in the formula, n equals n times 2 pi divided by omega naught. So 2 pi divided by omega naught is 3 and a over 3. Then we can read n equals to 3 over 8. And the least common multiplier is 24. Okay. And wall of text is a bit nicer than this. Okay. So here we kind of go slowly. Okay. So another way to see this is we kind of look at what are possible in here. Okay. So like for example on this part, so this e to a j 3 pi over 4 n part. Okay. So we want how should I say? We want this part to be some multiple of 2 pi, right? Okay. And because we once again want e to the j, this e to the j omega naught n should become multiple of 2 pi for this thing to like run back to the full circle. Right? So the idea is that you want this part to become multiple of 2 pi. Okay? And then you see what possible n will give you this as a 2 pi. And because you know this omega naught is a over 3 times is 2 pi divided by over 3. So you know if your n get an increment by a over 3, then this part will increase by 2 pi. But you see that a over 3 is not an integer. So you cannot have a over 3 as your n. So you just look over another. So it cannot be multiple of 2 pi. Then you see what if I want this to be multiple of 4 pi. So if you want this to be multiple of 4 pi, then you want to increase your n by 16 over 3. But you see 16 over 3 is still the other integer. Then finally you see that if you increase your n by 24 over 3, then this j 3 pi over 4 will increase by 3 pi because and your n actually increases by 24 over 3 is 8. So if you increase your n by 8 here, then you will increase your e to a j omega n by 6 pi, and 6 pi is 3 times 2 pi, and then see you got back to your full periodic. Okay, yeah. So that's what this wall of text saying, and so you see the period is 3 and 8, and you take the least common multiplier, then the full period is 24. Okay. Any questions so far? Yeah. So this is a very tricky part of the chapter, and no question for this example. Then I guess we can go to the next topic. Today is we should have time. We have 10 minutes, but it's not too bad. Okay, and so similar to continuous time, we also want to talk about harmonically related discrete periodic signal. Okay, so one is harmonical signals, and once again, the idea is we want signal with some common period n. And here we just kind of write our answer because it's very similar to continuous time. So your signal will be e to a j k times this kind of fundamental frequency related to the n. So, but we just write as 2 pi divided by n here. Okay? So e to a jk and 2 pi divided by n big N and your small n. Okay? So those are your harmonic signals. And k will be integers once again. So remember the idea was, the idea was you have some period and then you want to increase your signal to be, so the period is like this thing, and then you want to squeeze more and more period into this fixed big N period. Okay, but just like what we said before, for the frequency of a discrete signal, everything going over 2 pi doesn't make doesn't really make sense. Okay, so the frequency, which is k times 2 pi n here, if they go over 2 pi, then you are going back to the same frequency. Okay, and what that means here is that so this k times 2 pi divided by n divided by increase 2 pi means that basically means is k increased by n. So you can just see here. Okay. So this k, if you increase k by big N, then the signal will be e to the jk plus big N, and then 2 pi divided by n small n. And so move things around, you see this HR big N just give you e to the j big N and 2 pi divided by n. So big N cancel with big N. So it's just e to the j 2 pi and small n. And small n is an integer, so e to the j 2 pi n, this is just 1 always. Okay. So you see that if you increase n k by big N, then the signal is the same. So your k is also kind of periodic, because you increase k by big N, then you get back the same signal. So so they are actually only big N different signals. So only big N different k that give you a different signal. And so how you count them is really arbitrary, but this is a good convention. Okay? So you just count your k. Usually you just count k from 0 to n minus 1. But sometimes it will shift a little bit because, yeah. So I guess a good thing to say. So this is so this 0. So k from 0 to n minus 1, and then you also see that from this equation we have here. So you plus the big N is the same thing, then minus the big N is also the same thing. So sometimes we will also write negative k. So you have this psi n minus 1 equal to psi minus 2. Oh, sorry, psi minus 1. Okay. Yeah. So the convention really goes whatever that's convenient for us. Okay. So you can also have psi equal to psi minus 1, and which will equal to psi n minus 1. And yeah. And you can also have psi minus 2, psi minus 3, etc. Okay. And yeah. But you know, psi minus 2 equal to psi bigger minus 2, etc. Okay. And yeah, so that's the big N distinct signals, and let's see the picture. Okay. So k equals 0 is constant function as always. And yeah, it's really similar to before. Yeah, actually, we are using the same picture, just give them different different interpretation now. Okay. So those are the discrete time harmonic for n equal to 16. Okay. And okay. Actually, oh, did I make this wrong? No. Okay. Yeah. And k equal to 1. So you see that for this 16 here, we have this 4 period. And k equal to 2, then we have this 2 period here. So for continuous time, we are squeezing more period. And k equal to 4, then we are squeezing more and more period into this 16. And once again, and we see that when k equal to 8, which is actually about n over 2, we have the highest frequency. Okay. So when k equal to n over 2, then your signal is about e to the j pi n, and as we say, e to the j pi n is the highest possible frequency for this current signal. Okay. So k equal to n over 2, we have highest frequency, and then we see that with higher k, then our signal kind of go back. The frequency actually going lower, even though the continuous time the frequency just going higher. And 16 over 8, k equal 14, k equal 15. Then you see that k equals 16. Then we get back to the same signal as k equal to 0. Okay. And yeah, so k equal to 17, then it's same as k equal to 1, and k equal to 18 is same as k equal to 2. And k equal to 20, then it's same as k equal to 4. So yeah, so that's the discrete time harmonic signals. You see that you fix on common period n, and there are only n distinct harmonic related discrete periodic signal. Okay. and so you once again label it by n. Their formula is this e to the jk 2 pi divided by n small n. So this formula you should probably get familiar with. We are going to see them all the time, especially when we talk about Fourier series. And yeah, you need to remember that they are labeled by only n distinct case, and usually you just write. You can really start and finish at whatever n numbers, but usually you label them by n contiguous numbers. So this k can even be negative, so like -1, -2, -3. But yeah, convention is going from 0 to n-1. So here we see n 0 to n-1, then k from 0, 1, 2, 3 to 15. So those are the 15 harmonics. So big N equal to 16. Okay. I think we are about time, so we have 3 minutes left. But next time we are going to a very different topic. We are going to talk about impulse and unit step function. Yeah, today we finished this our discrete time, periodic functions, and harmonics signals. Okay. If no question, then we have no class this Friday, and I will see you on next Tuesday. Yeah. Okay. Yeah.
我想问，就是因为我刚刚听老师这样讲的话，
有没有懂吗？
因为我在想说 M 和 N，因为老师你刚刚说没有什么物理，可是
有啦，就是对啊，有物理，有一些物理意义吧，但是我不知道读物理就直接可能比较signal上意义。
对啊，所以意思说我可以猜说这个 M 啊，是等于是说一个周期可以取多少个点嘛？这个
一个周期可以取多少个点？
对，
不太像吧？
因为我刚刚听老师讲说是从这里去算这个有多少个点，像这个
M 比较像是说这边的一个周期对应到这边有多少个周期。对，对吧？是吧？我想想看，例如说这个东西吧，这个东西的，我想看，它 n 是2嘛 ，n 是2，这样。
那 n 是它要几个点才会正循环一次，然后 n 是它要循环一次中间会有几个点？
等一下，应该说我看一下，我找个比较好的。这个东西好了，这个应该是最好的。对，这个东西它的 m 是，这个东西它 m 是15，然后 n 是16，对，它16个点会循环一次，但这里正超多的，对吧？所以 n 是16，就是说这样子16个点你一个 period， 然后 m 是15，是说你这个 period 里面它这边会正15次。对，
那老师那个小 n 是什么？这个
小 n 是这个点啊，小 n 是你的 free variable 是这个轴。这个轴上你选什么点啊？这就是0、1、2、3吗？对啊，这个轴。小 n 是我们的 time variable。
那老师，那这个点啊，到底是指的是什么？就是这个取点到底是跟这个有什么关系？就是跟 continuous
就是没有，就是把这个 continuous 有点 same point 感觉嘛，就是 continuous 我们选在 integer point 选到这边点了。
然后接下来最后一个问题是，老师你是怎么样？那个就是你是怎么样算？就是刚刚不是有讲那个 example？
我应该把这 update。你要过头？这过头，这下一个礼拜。
就是刚
example 怎样？
对 example 就是你在讲说是
这个这1.6吗？
对，就是它怎么样子变到 n 加8？因为我有点搞不懂，
就是我就是说把它当做 continuous 碳算的话，如果这个 n 可以是 continuous number 的话，那 a/3 就会是一个 period， 对吧？那所以我们就这样去找，我们去找说，所以我希望这个东西2派嘛，2派的话，它的 a/3 会是一个 period， 但是 a over 3不可以是 discrete 和 secant 的 period， 因为它不是个 integer。所以我们去找下一个。那我如果要这个是 4 派的话，那它这里你要加16 over 3， 16分，对吧？那这个也不是一个 integer， 那我们就再找下一个。我要变6派的话，那这里要是24 over 3，那就会等于8这样子。所以就有点对应刚才那个 n 跟 n 的事情嘛。所以这里 n 是8，然后 m 是你找的34是3这样子。
哦，
对，
好，懂了，下一次。
不然说像这种时候，我是可以直接写它是或不是的，还是我要推导说它，就是我需要有那个推导过程，就它是periodic这种事情。
如果它是 periodic， 可能不太需要推导吧。但是我觉得你算一算，你去把 fundamental period 算好，应该算，你可以写一下那个算 fundamental period 的过程，应该就会有那个就有推导了。对，但是不是的话，你可能写一点理由会比较好这样。
哦，
对的。
那想问一下是说，像这里啊，像这题它是要 determine 那个 even 跟 output， 那我是要把它的那个式子写出来，就是这个图形的式子写出来。
不用吧？
不用，这夸张讲，
这还蛮麻烦，
对啊，
因为对啊，那不太好表示，而且我们还没有把那个要什么 state function 宣传的麻烦，对的，就不用写式子。
啊，我问一个要白学的问题，就是它这个 sampling rate 是和我们教的这些 frequency 有关系吗
？sampling rate 其实我没有，其实不太该讲 sampling 的，因为我们没有教 sampling 的，但 sampling rate 基本上是 integer 啦。我是用 sampling 来讲说我们从这边这个，那么 n 就是取 integer 这样 ，rate 是 fix 的，因为我们就说 discrete signal 我们就永远都是取 integer point 这样。对。
那这边像这边是，就是它是依照这个间隔来作为单位，还是？
对，就是永远是以这个 integer 间隔为单位，就是我们每次都是每个 integer 选一个点的。
像这边就是大概是以每
就是每一，不管怎样，每次都是每一个的。
然后那我们下面的这个 S 轴是什么？是
X 轴就是对啊，是时间，这是时间。对啊，就是小 n 在小 n 我们当做时间的。
把这两个当成同一个。
我们都当做时间的。但是对啊，是有点，我们现在这里有点像是把它们当一样的东西，然后这里就只取 integer 的点，然后看会发生它会变成什么 signal 这样。
好，